Hello and welcome again to lectures on state space approach to control system analysis and design. We will continue our discussions on controllability. So far we have studied the Kalman's controllability criterion and the method to determine the input for achieving the required state transfer. We have discussed algebraic controllability criterion, in which we tested the rank of one n by n matrix, and thereafter we discussed controllability subspace and stabilizability. We also discussed how to decompose an uncontrollable system into a fully controllable system and a fully uncontrollable system. Now the topic today is to study the controllability criteria based on transformation into diagonal form, which is Gilbert's controllability criteria, and the same thing is generalized to the case of repeated eigenvalues, which is Jordan form, and then other one is Haughton's criteria, which is based on the test of rank of some smaller order matrices. So with that we proceed ahead. Before we actually discuss the Gilbert's criterion, we first see that the controllability of a linear time invariant system remains invariant under a linear transformation. And to prove this, we consider the dynamic system given as x dot equal to ax plus bu, where the system matrix is A and the input matrix is B. Through a similarity transformation x equal to tz, this system is converted to an equivalent system z dot equal to fz plus gu. The matrices characterizing the system here are f and G. Now what we do is, we know that these matrices F and G are related to A and B through this transformation, and of course that A will be related to F other way around, so A can be written as TFT inverse and B can be written as TG. So if we consider the controllability matrix of the system x dot equal to ax plus bu, where the system matrix is A and the input matrix is B, it will be given by B, then AB, then A square B, etc. up to an minus 1B, and in that some term in the middle is AKB. Now what we do is that we consider that this A is related to F as TFT inverse and B is related to G as T into G. So we make these substitutions. In place of B we substitute T into G, and in place of A we substitute TFT inverse, and of course in place of B TG. So in this manner, throughout in this, we make substitution. In place of A, TFT inverse, and in place of B, T into G. And then we concentrate on this term, that A power K B. And we see that A power K B was this, and in that, if we expand it, then it is TFT inverse, multiplied again by TFT inverse, multiplied again by TFT inverse. In this manner it is multiplied k times, and finally it is post multiplied by TG. Now what we see, that this T inverse cancels with this T inverse cancels with this one with the next T, and so on, and we are only left with T f power k into G. T on the left is left and G on the right is left. All other these matrices they cancel with the following T. So Tf T inverse power k Tg becomes Tf k power T f power k g, and that means that the Q matrix becomes T pre-multiplying this matrix G, Fg, F square G, etc. up to Fn minus 1G. And this matrix we recognize, this is the controllability matrix of the transformed system. So the controllability matrix of original system is T times the controllability matrix of the transformed system, the system Fg. So we got from Q the matrix T into the Q bar, and because T is a full rank matrix, it is a transformation, so that means rank of Q should be equal to rank of Q bar. Now we proceed starting from the system matrix F and G, that transformed system, and for that we have Q bar given by this expression. Again we make substitutions. In place of F, T inverse AT, and in place of G, T inverse B. And then we can show that this Q bar is T inverse times Q. And again, because T inverse is inverse of the similarity transformation matrix T, so rank of Q bar will be the same as rank of Q, T inverse being the full rank matrix. So we have proved both that rank of Q is rank of Q bar and rank of Q bar as rank of Q. So we can say that the controllability remains invariant under any linear transformation. Now that means that sometimes if it is mathematically convenient, we can check the controllability of the transformed system instead of the controllability of the original system to have mathematical ease of mathematical manipulations. So Gilbert controllability criterion offers ease for testing the controllability in the case of linear time invariant systems. And the system originally may be available in diagonal form. If it is not, we can transform the given system to diagonal form. Z dot equal to lambda Z plus beta U. Lambda is a diagonal matrix in which the diagonal entries are eigenvalues of the matrix A, and beta is the corresponding input matrix corresponding to the diagonal form representation. Now, as I said, either the system may be available in the diagonal form or it can be transformed into the diagonal form. Then we can apply the Gilbert's criterion, which is stated here. According to the Gilbert's controllability criterion, the system in this diagonal form Z dot equal to lambda Z plus beta U is controllable if and only if the beta matrix has no rows which are 0. All the entries in any row of beta matrix should not be 0. At least some entries should be non-zero. Then the system expressed in diagonal form will be controllable. And if any row consists of all entries as 0, then the system will be uncontrollable. Now we see the same expression explicitly, that lambda consists of the eigenvalues along the diagonal, lambda 1, lambda 2, etc. and rest of the entries in the matrix are 0. And the corresponding input matrix is, this is the row of, first row of beta matrix, which is denoted as beta 1. This is the second row of beta matrix, denoted as beta 2, and so on. Now if any ith row is 0, then what will happen? Then the solution of the state, which is expressed by this expression, it is state transition matrix evaluated between t and t naught, multiplying the initial state plus the integral of the state transition matrix into this elements of that ith row. So for example, if you consider beta 1 row, then beta 11, beta 12, etc. ith row, beta I1 into the first input, beta I2 into the second input, and so on. These all contributions taken together are to be integrated between T0 to T. Now what happens if entire row is 0? That means beta I1 is 0, beta I2 is 0, and so on. All elements up to beta Im is 0. Now what it means? That input is not reaching the corresponding solution. That contribution is not reaching. Whatever left is only this much. That input contribution is not reaching, and obviously that state transfer cannot be achieved. And that proves that Gilbert's controllability criterion, that state transfer will not be possible if all entries in a row of the system in the diagonal form are 0, or there should not be any 0 row in the input matrix of the diagonalized system or the diagonal system for controllability of the system. This is the Gilbert's criterion. This is already stated. So if any row of beta, say jth row, is 0, then the corresponding eigenvalue lambda j will be treated as uncontrollable eigenvalue, and the corresponding mode e power lambda j t, this one, is the mode which is uncontrollable. So Gilbert's controllability criterion gives precisely that which eigenvalues or which modes are controllable and which are not controllable, and it helps us to separate already the controllable component of the system and uncontrollable component of the system. We look at one example. This example is taken from Friedland's book. This is the way it is given, in which you see A matrix is a full matrix like this, only a few entries are 0, and B matrix is like this. Now using the transformation, for seeing the transformation, I suggest you to look into the book on the chapter controllability and observability, and in the initial portion itself you will find that transformation which can convert this system to this system when that x equal to tz is used. And so we obtain the corresponding system in the diagonal form, the equivalent system in the diagonal form. The diagonal entries are the eigenvalues -1, -2, -3 and -4. And the corresponding system matrix, this is the T inverse B matrix, is obtained as 1, 0, 1 and 0. 2 entries are non-zero and 2 entries are 0. Now obviously, because this corresponding to this eigenvalue -2, the row, here it is only one element because there is single input, this row is 0, so this -2 is uncontrollable. For the same reason, this eigenvalue -4 is also uncontrollable, and so this system is uncontrollable because of two uncontrollable eigenvalues. The controllability subspace here will be of dimension 2, and if it is decomposed into controllable and uncontrollable, controllable system will be of order 2, uncontrollable system will also be of order 2. Now we consider the generalization of Gilbert's criterion for the case of repeated eigenvalues, and here what we obtain is Jordan form matrix, and each Jordan block is of this, either of this type, in which the diagonal elements are the same as the eigenvalue which is repeated a few times, so the order is that time of the repetition, and then the elements at the sub diagonal is unity. This is one form. Other form which may be obtained depending upon if the generalized eigenvectors are arranged one way, we will get this. If they are arranged differently, then we will get this, in which the eigenvalues will still be on the diagonal. However, the entries are on the upper diagonal. That will be unity. Now, for both the things, criterion is simple. If it is the one in which lower diagonal has entries 1, lower subdiagonal has unity, then this system will be controllable if the first row in beta of each Jordan block is non-zero. If I go back, that means this in the corresponding beta matrix, it is not shown here, that first entry, so entry corresponding to this, the one along this, that row should be non-zero. And in this one, the last one we have to see. So in one case we have to see the first row, and when it is the upper subdiagonal, the upper one, then we have to see the last row corresponding to the Jordan block in the beta matrix, that should be non-zero, and then the system will be controllable. Now again, the eigenvalue corresponding to which the beta has that particular row 0, that eigenvalue is uncontrollable eigenvalue. And the modes in this case, e power lambda j t e power lambda j t, and so on up to t power nu j e power lambda j t. This nu j is the repetition of the eigenvalue lambda j. So we have seen that in case of Jordan block matrices, when we solve, we get e power lambda t, t e power lambda t, t square e power lambda t, and so on as the modes. So all these corresponding modes for the eigenvalue lambda j will be uncontrollable if the eigenvalue lambda j is uncontrollable. So again, here also we get specific information about which modes are controllable, which eigenvalues are controllable, and which eigenvalues or modes are uncontrollable. Now we can see the ease with which the diagonal representation of the system helps to identify the controllability and also the Jordan form. Now this Haughton's controllability, this is also applicable to linear time invariant system like the algebraic or the Gilbert's criterion was. They were applicable to linear time invariant systems. The Haughton's controllability criterion is also applicable to linear time invariant systems. And according to this criterion, this system, this need not be in any particular form. A matrix can be in any form, need not be diagonalized, need not be made into companion form, etc. So this system is controllable if we have to assemble this matrix. The first part of this matrix, first n by n component, is lambda I minus a. We are checking the controllability of ith eigenvalue. So ith eigenvalue is controllable if rank of this matrix, in which the first part is lambda I minus a and the second part is entire B matrix put as it is. So first n columns are same as columns of lambda I minus a, and next m columns are the columns of matrix B, all the columns of B. So this matrix is n by n plus m. There are n rows and n plus m columns. If the rank of this n by n plus m matrix is n, then the ith eigenvalue is controllable. And if it holds good for all eigenvalues, then the system is controllable. So this Haughton's controllability criterion is based on rank test of a smaller size matrix. We know that controllability matrix has size n by nm. That is huge. Here it is, instead of the product nm, it is n plus m. This matrix is of a smaller size. However, we have to do the rank test multiple times. In case of the rank test of controllability matrix, we require testing only once. However, in this case, we have to do this testing k times if there are k distinct eigenvalues. So if there are all eigenvalues are distinct, then it will be n times, and if some eigenvalues are repeated, then for repeated eigenvalues it has to be done only once. For each repeated eigenvalue, only once. So it will be required to be done a fewer times. So this is the advantage, and it is based on the rank test, which is simpler to do. Also, there is no transformation involved. Only the eigenvalues are to be evaluated. So the eigenvalue lambda j, supposing that system is uncontrollable, then all those eigenvalues lambda j for which the rank of this matrix comes out to be less than n, they represent the uncontrollable eigenvalues. And accordingly, e power lambda j t, or if it is repeated, then e power lambda j t along with t e power lambda j t, etc. will be the uncontrollable modes. So that is the Hautas criterion, and we look at one example. We consider this third order system. By inspection, we see, because it is lower triangular, the eigenvalues are -1, -2 and -3. And the system, the input matrix is 1, 0, 1. So we check, as I said, eigenvalues are -1, -2 and -3. We check the controllability of the eigenvalue lambda 1 equal to -1. And so what we do, we evaluate lambda 1 I minus a, and this one is this, with this a. So lambda 1 I minus a is this matrix, and with that we put this B matrix here. So we have this lambda I minus a, lambda 1 I minus a, and this the full B matrix, which of course here is just a single column, it is a single input situation. And we check the rank of this, we will find that its rank is 3. We check similarly for lambda 2 equal to -2. We have already established that lambda equal to -1 is controllable. So we check that whether lambda 2 equal to -2 is controllable in the same manner, and the answer comes yes, the eigenvalue -2 is also controllable. We check for the third eigenvalue lambda 3 equal to -3, and we will find that this eigenvalue comes to be uncontrollable. So because 2 of the 3 eigenvalues are controllable, this system is uncontrollable. One eigenvalue is not controllable, so this system is uncontrollable. That is the conclusion. And the mode e power lambda 3t, or which is e power -3t, is the uncontrollable mode. Now because this is stable, e power minus lambda 3t will decay with time and it will reach the origin. It will become 0 as t tends to infinity. So this system is uncontrollable but stabilizable. We summarize this lecture. As we have seen, the controllability test based on Gilbert's and Hautas criteria are simpler to perform. In Gilbert's case, it is just by inspection. In Hautas' case, it is by determining the rank of a much smaller matrix than the rank of the controllability matrix. Of course, in case of application of Gilbert's criterion, we have to transform the system into diagonal form or the Jordan form, depending upon whether the eigenvalues are distinct or repeated. That may require considerable effort to convert into the diagonal or Jordan form. Otherwise, application of criterion is simple. Haughton's criterion doesn't even require that. So Haughton's criterion is even simpler. And another aspect which happens in case of that rank test of full controllability matrix is that if the elements of A are such that some elements are large and some elements are small, then A square will have some elements even of larger order. A cube will have even of larger order than A square and so on. So what will happen? The matrix, the controllability matrix B, A, B, A square B, when you solve some examples, you will see that it successively results into very larger numbers, or in case the elements were small, then very smaller numbers. And that causes numerical ill conditioning of the matrix, thereby rank test becomes difficult. Theoretically, it should hold, but because computations have limited precision, so numerical ill conditioning happens, and an uncontrollable matrix, a controllable matrix may be shown as uncontrollable. The rank may be shown as theoretically different from the theoretical rank of the matrix. This may happen. So in practice, I have seen that instead of rank test of Q, testing the rank of smaller order matrices, as in case of Haughton's, gives better conclusions about the controllability of the system. And of course, the Gilbert's and Haughton's methods, they give also the uncontrollable eigenvalues and uncontrollable modes. That is another advantage that comes. So we have seen so far that for linear time invariant systems, the alternative methods like algebraic test, Gilbert test, or Haughton's test, they are simpler to perform. They don't require product of so many matrices, state transition matrix to input, etc., and integration. Much simpler compared to Kalman controllability criteria. However, in case of time varying systems, we don't have to choice. We don't have any choice. We have to apply the Kalman's controllability criteria. Thank you. See you again in our next lecture.